Yes.
I need to tell you about the...
Okay, it's a pleasure to introduce Amanda Luby, who's a PhD student at Carnegie Mellon, with her under the advice of Steve Feinberg, who is greatly missed at this conference. And please, she will be talking about a graphical model approach to eyewitness identification. Thank you.
Thank you. Good morning, everybody. I'm really excited to be here and share this work for you. Just wanted to thank the organizers for a great conference and all of the other speakers for some great presentations as well. So I started this work about 2 years ago as a first-year PhD student doing an advanced data analysis project. So kind of keep that in mind as the main motivation for the work that I'm presenting so far. So short introduction, I will be talking about eyewitness identification versus eyewitness testimony. So I would kind of draw the line between testimony as, what did I see this person doing? Versus I'm talking more about eyewitness identification. So say, I see someone doing something, but they're a stranger to me, and can I pick them out of a lineup? So more of the perpetrators not known to the witness. This is all strangers in kind of a lineup task in, say, a police department. And this is a big deal in a study of 300 DNA exonerations by the Innocence Project in the United States. False identifications were a factor in over 70% of those exonerations. So this is a real problem because people are very bad at remembering things. They think that they remember a person very well, but then they don't. They screw it up. But also people believe each other. It's just kind of how humans work. And so if someone tells a jury that I saw this person doing this thing, you just naturally believe them, even if you know that their memory probably isn't as good as they think that it is. Eyewitness identification was identified as a leading factor of wrongful convictions all the way back to 1932, so almost a century ago. And it's been an active research area in psychology for the last 3 decades. So it might seem like a pretty simple task at first, here are some people, do you pick the right one or not? But there's actually a lot of variables associated with lineups. So there's the presentation method, so simultaneous versus sequential. So in a simultaneous lineup, you see all of the options at once, and you pick the person that you saw do it or not, versus sequential, you see one person at a time and are asked to decide if that's the person that you saw or not. There's also instructions that the witness is given by the police department. So I'll talk about these in the case of biased instructions, we call them. So that would be choose the person that you saw the scene at the crime, which kind of implies that the actual person is in the lineup, versus unbiased instructions, which is more like the perpetrator may or may not be present in the lineup. So you're given an explicit option to say that the person is not in the lineup. There's other things like retention intervals, so how much time has passed between the observation of the crime and the lineup. How many known innocent people do we put into the lineup? Should it be 6 people, 8 people, 5 people, 2 people? How do we pick the other people who go into the lineup? So we call these fillers. So those are the people who are known to be innocent. There's also types of crimes, so maybe a violent crime versus a theft. There's the type of interaction with the perpetrator. So were you a witness or were you the victim? That's going to change the way people remember things. And then there's also things like lighting at the time of the crime, the distance that the witness was from the scene of the crime, and then things like race, gender, and age differences. All we know have an effect on human memory, and therefore eyewitness identification. So there are a few things that almost everybody agrees upon. I took this from the Innocence Project website, and it was also mentioned in the National Academy of Sciences report. So things like blind administration. So the person who is giving the lineup should not know who the suspect is and who the fillers are. The lineup composition, you shouldn't have just one person of a different race and then all the rest the same race, because that person will stand out. Instructions, so you should get the unbiased instructions, which I mentioned before, and then also you should record a confidence statement at the time of the lineup. So this is to kind of counteract, as people go through the lineup in their head, they become more and more confident in their decision. And so a confidence statement is a way to really record their initial feeling about their identification at the time. And then finally, all lineups should be recorded. We should have evidence that the lineup was given fairly, they weren't given any hints, and all of the things like that. But there's also a lot that we're still arguing about. So for instance, the simultaneous versus sequential presentation, this has really come up in the literature maybe the last 4 or 5 years or so. And pretty big issue. There's also maybe a bigger issue is how do you choose the fillers? Is it someone paging through pictures of people and then picking the ones that they think are the most similar? Should we have some sort of system? Should we have multiple people picking the fillers, etc.? And then also, what's the role of non-system variables? So these are the variables that we can't ever control. So things like race, gender, age, type of crime, lighting. Basically anything about the witness or the perpetrator or the crime that we know has an effect and we can't control. So we know that these things have an effect, but then what do? Do we just not let some people participate in eyewitness identification? Do we draw the line somewhere? How do we deal with those things? So an intuitive model, I apologize for the text getting a little screwed up. So we have system variables, so these are the things about the lineup, the presentation, the instructions, the blind administration that we can control. There's also, variables about the witness. So this is, we've heard a little bit from some other talks about, is the witness reliable? What are the things about the witness that may have an effect on their identification? And then also variables about the crime. So this would be the things I mentioned, like the type of crime, the distance, the lighting, etc. So intuitively, we think that all of these variables have an impact on the lineup outcome, and the question is kind of how do they work together and what effects do they have? So this work that I'm going to kind of shift into now about the data analysis was really inspired by this National Academy of Sciences report identifying the culprit, in which they made a series of recommendations to law enforcement, research communities, judges, juries, lawyers, and one of the recommendations was a broad exploration of the merits of different statistical tools for use in the evaluation of eyewitness performance. So that's what got this project going and what my data analysis work was about, so that's what I'll be talking about now. So the current methods that I see a lot in the literature are a diagnosticity ratio, which is a likelihood ratio, and an ROC curve. So the way that they define diagnosticity ratio is the probability that the suspect was identified given they're guilty over the probability that the suspect was identified given that they're innocent. So in every lineup, it can either be target present, so that means that the actual perpetrator is in the lineup, and so that would be the numerator of the diagnosticity ratio, or the lineup can be target absent, so they can have the wrong person in the lineup. And so the denominator of the diagnosticity ratio is the probability that they identify the innocent suspect. And recently there's been a push to adopt an ROC curve because it does kind of have this natural connection to the diagnosticity ratio. So there's a true positive, which would be identifying the guilty suspect, and then a false positive, which would be identifying an innocent suspect. And then the way they do the curve is by confidence level. So if you're familiar with ROC curves in classification algorithms, there's usually some sort of parameter that we vary to kind of measure where is the cutoff between doing pretty well and not doing well. And so in this case, we use the expressed confidence level. So usually in a 1 to 7 or 1 to 10 scale, and so each of the confidence levels represents a point on the ROC curve. So I have a couple issues with both of these methods, which I'll talk about now. So the first is that the diagnosticity ratio may oversimplify the lineup data. So this is just a toy example. So let's say we do 2 different procedures and we want to know which one is better. So in the first procedure, let's say we have 50 target absent lineups, 50 target present lineups, and we get 25 true positives and 15 false positives. So that gives us a diagnosticity ratio of 1.67.
Can I just ask, there's two ways of identifying the wrong person. One is the person isn't there in the first place, and the other is that he is there but somebody else is identified.
Right.
Separate those out?
Yes, so I'm treating false positives as a target absent lineup, so he's not there, and they pick the innocent suspect.
Anybody?
Or just the innocent one, not one of the fillers in the target absent lineup.
But he wasn't there in the first place.
Right, but the police.
They're all innocent.
Right, so they're all innocent, but the police know that n minus one of them are innocent, and there's one that they think is guilty but is actually innocent.
They have put a suspect in there, so the police think that's who it is.
Right.
Oh, there's always a suspect.
Right.
If you pick somebody that the police think is innocent, then that counts.
Right.
Okay.
Right.
And the suspect is actually factually innocent.
So when you say target absent, he's not actually absent. It's just the guilty person is absent.
Right. Right. Yes. The target is still there. Yes.
I get
yes.
you.
Yes.
How is it decided whether someone is guilty?
Oh, so this is all in an experimental setting. So you create the crime. You know exactly who the suspect is. You create the lineup. You know if the person is guilty or not.
Just one thing you said, that the people give their confidence statement. Is that on a numerical scale, on a verbal scale? How are the scales chosen?
So it really depends. I found that in a lot of the experimental literature, it's a numeric scale, but I think a lot of times in practice, it's are you really less or like in the middle confident? So it really depends. It's really not unified across different disciplines or different jurisdictions.
Yeah, so when you're saying true positive, they might be a measure on that scale,
it could
right?
still be a guess, yeah. So they could be zero, they could say, I'm not confident at all, but
I
they
choose
guess
that
and
person.
pick the right person, and that still counts as a true positive.
As a true positive.
Right. So let's say you do the first line of procedure and get this diagnosticity ratio. You do the second line of procedure, and maybe you tell the witness, whoever you pick is going to get the death penalty. And so they might be, a little scared to pick someone. So then in this experiment, you only get 6 true positives and 2 false positives. So that leads to a diagnosticity ratio of 3, which is higher than 1.67. So you would conclude that the lineup procedure 2 is better. And I think there's a lot of problems with that because there's a lot that you're missing because both the true positive rate and the false positive rate are much lower. And so that might not actually be what you want. But by just looking at the diagnosticity ratio and just publishing that, you're really missing all of that information. And some problems that I have with the ROC analysis, I think really boil down to this problem that there's an inherent structure to a lineup, and by putting something into a 2x2 classification, you're missing a lot of it. So an ROC curve naturally just makes things a 2x2 classification. So you have true positives and false positives, false negatives and true negatives. That's all you can have in an ROC curve. But in a lineup, you have these filler identifications which have distinct consequences. So if you identify a filler in a target present lineup, so when the actual perpetrator is in the lineup and you identify a filler, it's kind of like a false negative because you're letting the actual guilty person get away. Versus a filler identification in a target absent lineup, that's kind of what the lineup is supposed to do, is you're supposed to take away the chance of like picking the wrong person. So there it is a true negative, kind of. But a lot of people have a problem with a positive identification and treating it as a negative. So they're saying the person is there, they're wrong, so the consequences are the same as a negative, but it's not actually like a rejection of the lineup. And so I think it's really important to kind of maintain this structure and not lose any of this information in any analysis method that we do use.
The reject lineup means saying nobody's there. The person is not there at all.
Right, so that would be the reject lineup. So you look at the lineup and you say the person is not there. One of the, I'll go into a little more detail now about specific problems with the ROC curve. So here are two different ROC curves. I used the exact same data. On the left, I calculated the false positive rate just by the amount of times that the innocent suspect was identified in the absent lineups. So you see it's very far to the left, not so high, versus if I treat the false alarm rate as just any time that the witness says someone was there and they were wrong. And then we see the ROC curve drastically change. It takes up a lot more of the space, both in the X and Y directions. And also, it might be a little hard to see, but on the left, the blue dots are higher up. So we would say that that procedure is better, versus on the right, it switches. And so this really isn't ideal, especially if people aren't super careful about which method they're using to calculate the false alarm rate. You know, we just don't know which one they use, and it switches the interpretation and the conclusions of the experiment, which is not good.
And the different points belong to different degrees of confidence?
Yes. Mm-hmm. Right. So the taller points are basically all of the confidences. So there's a higher hit rate and a higher false alarm rate, versus the high confidences are more to the bottom because you're getting less of the true positives, but also less of the false positives. Another issue which has started to be addressed in the literature a lot more is that there's uncertainty in these points because you are taking a sample, you're doing an experiment, and then you're calculating this proportion and you're plotting it. So these are proportions from a sample, so they have some uncertainty associated with them. You can't see the band so much. Sorry. So the middle graph should have confidence bands in gray around them. And I wanted to show you both the confidence bands and kind of the hash marks because there's uncertainty in both the X and the Y direction. So sometimes you might miss overlapping in the X direction because we're so used to looking at Y direction. So it's really important to notice that even if they overlap in the false alarm rate, the curves are still indistinguishable. Also these are just binomial confidence intervals, so it's very optimistic and there's no way that's actually what the confidence looks like. And kind of the final issue that I want to talk about with ROC curves is that it restricts your comparisons to two quantities. So you have your hit rate and your false alarm rate, and that's all you get. Another thing you might be interested in is what's the probability that you identify the guilty person given that you made an identification. So that would be the positive predictive value or the false omission rate. So given that you rejected the lineup, what's the probability you were right? And since we have this 2x3 classification, there's no way to go from the ROC curve to this positive predictive value chart that I show. So it is an important thing to keep in mind that once you make this graph and you take away the table, there's no way to get back to the table because it does have 3 columns instead of just 2. So how do we fix it? My first thought on how to approach this, with some guidance from Steve Feinberg, of course, is to start with the table that we think the structure follows and then just add more variables and treat it as a contingency table. So now instead of a table, we have a multi-dimensional hypercube for each of the variables that we have in the lineups. So I'll treat it, so we have a 2x3 by 11 by 2 contingency table. So the 2 is whether the perpetrator is in the lineup or not. Witness choice, so did they identify the filler, identify the suspect, or reject the lineup. Confidence, so 0 to 10 scale here, and then also instructions, so did they get the biased instructions or the unbiased instructions. And I think this is a good way to look at it, at least to start with, because you can add more dimensions without changing the theory. This is categorical data analysis 101. It's well developed. It's great. So I kind of detail how I do the hierarchical model search on the training set and fit some expected values and then some goodness of fit tests. And then what's really important is that we make conclusions based on the variables and edges included in the model and their corresponding parameters, rather than just a couple quantities that we calculate. So after I did this, the first thing I do is, okay, do the expected values make sense? Did I screw it up? And no, I don't think I did. Because we don't really, so these are the expected values from the model using the log linear model. So we don't really see a difference between the two methods in, let's see, what button was it? The correct ID or the innocent identification. Just kind of what we would expect. Like instructions probably shouldn't change how well people remember the perpetrator. But we do see differences in the correct rejection and the false rejection. So
What's the response we're looking at here?
oh, so these are the frequencies. The frequencies. Mm-hmm. So this is out of, let's see, I think it was 1,200. Maybe those numbers make sense. So out of the sample that we have, how many would we expect to be correct identifications using the model? So this really makes sense because we see that the unbiased instructions in both of the reject categories are higher than the biased instructions, which makes sense because they're the ones who are given the explicit option that the perpetrator may not be there. So if you're told the perpetrator may not be in the lineup, you're more likely to not pick someone. And so we see that reflected, and we also see that reflected in the filler identifications. So the people who got the biased instructions, so they just heard pick the person you saw in doing the crime. They're more likely to pick a filler. So this makes sense. And we can represent the model with some parameters, but also with a graph, which is great when you're dealing with people who aren't statisticians, who are the people who are actually doing this stuff. So this is not a Bayes net. This is a log linear model. So each of the circles is a variable that's included in the model, and then each of the lines is an interaction term between those two variables that's included in the model. So what this tells us is that there is an interaction between witness choice and all of the other variables included in the model. So whether they pick a suspect, pick a filler, or reject the identification, we have to take into account the confidence level, the instructions, and whether or not it was target absent or target present. So, oh man, I didn't think I would have this much trouble with gray, but this circle is supposed to be gray because that's the one that we don't actually know in the real world. We know it in experiments, but that's the one, if you did this in the real world, you wouldn't know whether or not the perpetrator was in the lineup. And the model, here's the model, so the log of the counts is a linear expression, which is why it's a log linear model. Each of the alphas represents a circle, and then each of the betas represents a line. So what if we did a different experiment? So the data that I looked at, they had subjects watch a video that included a thief and a waiter. So I think it was like a credit card theft. So a waiter had left a card sitting on the table, and then someone came by and grabbed it. And so they asked subjects to identify both the thief and the waiter. So this is the waiter. I think this is the waiter lineup. And so here I found an edge between instructions and express confidence level, which wasn't there in the original. So this isn't great because we would want.
What's the extra term?
The extra term is the extra line. So it's the interaction
I care about
between.
lines, I care about the terms at the top.
Right, right.
It's that.
Yep, so this beta IC stands for the interaction term between instructions and confidence. So it's this line.
Right.
And they're just two-factor interactions, aren't you?
Right, right. Mm-hmm. I looked a little bit at three-term interactions, but when you only have 4 variables, it didn't make that much of a difference. And so this is kind of a problem because we would like to have the same graph for the same variables regardless of the experiment. But we can reconcile that just by adding another node. Because the experiment's a binary variable, and so we can just account for the interaction that was there between instructions and the expressed confidence level with this new variable and 2 interaction terms.
So what are the values for experiment?
So the experiment would be whether we had the thief lineup or the waiter lineup. So if you did, a larger experiment with many different lineups, then we could have, experiment 1, experiment 2, experiment 3. So that's going to, blow up the terms in the model, but at least it's there. Okay, so now I'm going to illustrate a couple of ways that I think the log linear model really does tell us some more information than what we're used to. So we've seen this before. This is the structure that I think lineups really follow. This 2x3 classification, which is great. But what's commonly implemented in practice is that there is no innocent suspect in the experiments. So they don't, a lot of times they won't say, okay, this is the person we're going to put into the lineups and pretend that that's who the police think did it, and they're actually innocent. They usually just, put a bunch of fillers in, and then afterwards, you assume that the innocent suspect would be chosen from the filler identifications uniformly at random. So if you have 6 people in the lineup, you would transform this structure into 1/6 of the filler identifications and 5/6 of the filler identifications. So one thing that I wanted to make sure of was that, and this is the way that the data that I analyzed came out. So this is the data that I used, and I wanted to make sure that the results that I were getting weren't dependent on whether this was 1/6 or if it was really a half, or if you had a different innocent person in the lineups, whether they'd be chosen more often or less often. So I wanted to make sure that the model isn't super sensitive to that. So here are some ROC curves with different fractions of the filler identifications being treated as the innocent suspect. So here's 1/10, 1/6, 1/3, and 1/2. And so you can see the only thing that really changes is the curve takes up different amount of space on the ROC space. But this would also change what your confidence intervals would look like and things like that. And so, but we see, so I fit the log linear model to each of these cases. So calculating the innocent suspect by 1/10, 1/6, 1/3, and 1/2. And got G-squared values, so this is the goodness of fit test, in the 60s, which is great because anything less than 100 in this case for the amount of variables that I have is a good fit. So we see that the log linear model has some flexibility that the ROC curves really don't in this case. Also, the model can handle variation in confidence. So on the ROC curve, each of the points represents the different expressed confidence level of the witness at the time of the identification. But if I do the same lineup every day, my confidence isn't going to be exactly the same. I don't think, expressing your confidence is a constant. It's going to vary. Everyone's is going to be different. If I said I'm like 50% confident, even if someone else was the exact same true value of confidence, they might express it in a different way. So I just wanted to see what would happen with a simple simulation study. So I assumed confidence statements follow some probability distribution, and then I simulated new confidence statements for each of the observations. So each person, I kind of put a prior on their confidence statements, and then simulated a new confidence statement from that distribution. I plotted the new ROC curve, and then fit the original log linear model and calculated the G-squared. So this is a situation that, just for illustrative purposes, the express confidence level has very small variance. So I said, okay, 10% of the time, the confidence will be the one lower than was observed, and 10% of the time it'll be one higher than what was observed, and then 80% of the time it's going to be exactly the same. So here are the ROC curves that we get, and you see there's still a bit of a gap right here, but it's unclear here and here if there's overlap, and this is without any sort of uncertainty included. So it's really hard to distinguish between the two methods this way.
What do the two colors represent?
The two colors are the unbiased and the biased instructions. And so out of 1,000 simulations, the model never failed to fit. So I never saw a g-squared that was higher than 100-ish, which is good. And then if the express confidence level has higher variance, the ROC curves become even more overlapped and hard to tell the difference between the two procedures. So here what I did, what I mean by high variance, is that 20% of the time the confidence was 20 points below the observed, 20% of the time it was 10 below the observed, 20% of the time it was the same, 20% of the time it was 10 higher than the observed, and 20% of the time it was 20 higher than the observed. So equal chance of being over a larger window. Okay. Another nice thing I think that the log linear model has is that as the complexity of the experiment and the data increases, the graph interpretation remains the same. So this is an ROC curve. I forgot to put the citation, but it's a Carlson and Carlson paper from 2014. So it's an experiment where they tested whether or not a weapon was present in the crime, and then whether or not the perpetrator had an identifying feature. So if they had, you know, like big black glasses or a mustache or something. And it might be a little hard to see in the back, but this top curve is no weapon, no feature. The middle curve is weapon and feature. The second lowest curve is weapon, no feature. And the bottom curve is no weapon and feature. So even if we just have two binary variables, so whether or not the weapon was there and whether or not the feature was there, it becomes much harder to kind of interpret what these different curves mean and which procedure is better and what the effect of changing one of those variables is. Versus this is I don't have the data, so I completely made up this, this model. So the solid lines are what I observed from the data that I have, and I also know that there's a solid line between, well, I don't know, but I suspect, strongly suspect, there's a solid line between distinct feature and weapon present, because whichever curve is on the top between the two changes based on what the other variable is. So this would suggest that if we took this data and made it into a log linear model, we would need an interaction term between weapon and feature, which is a little hard to tell just from this curve. And if you imagine that, you know, each of these variables takes two values, you're going to have a ton of different curves on your ROC graph, and it's going to be hard to kind of pick out what the effects of certain interactions are. So what about the other variables? So at the beginning, I kind of said, you know, we have lineup variables or system variables, variables about the witness, and then variables about the crime. So maybe the log linear model, let's say we did an experiment or, you know, had some great data from the real world that took into account all these things, which we don't. So here are the variables about the lineup, and then here are the variables about the crime that I've identified as kind of main ones that you see in the literature. And then witness variables, which I didn't really know what to put in there, but those could be things about that we've heard other people talk about the reliability of the witness, the memory of the witness, you know, whether or not they were under the influence at the time of the crime and things like that. And probably a lot of these variables have an effect on the witness choice, and then all of it together influences what would, in the bigger picture, would influence whether or not we think that the suspect is guilty. So how could this fit in with other forensic analysis? You might recognize this graph from way back when on Monday, Phil David's talk. So we had some fiber evidence, some blood evidence, and some eyewitness evidence. And this is a Bayes net, so we all know what it is. So I think that this experimental work goes in with this eyewitness evidence, but what's included so far is the eyewitness testimony. So what did they see the person doing? What did they observe about the crime? And I think we could use some more variables about the identification. So do we think that they got the right person? And that is how this work could kind of fit in the broader picture of kind of determining whether or not a suspect is guilty. Another thing I've been thinking about but haven't really done anything is what about if the lineup is an investigative tool versus kind of confirmation evidence? So do you start with some evidence that leads you to a suspect and then you do a lineup to confirm? That's going to be one thing versus if you start with a lineup, a witness says they saw someone, you just find a suspect that looks like that person and do the lineup, and then you find a suspect, and then you find some evidence. How do these things kind of depend on each other, and should we change the analysis of either based on one happening before the other? So currently I'm working with a professor in the social and decision sciences department at CMU, Cleotilde Gonzalez, and Stephen Feinberg again on some experimental design. We have support from the Arnold Foundation, and kind of the goals of doing more experiments are to be fully documented. So which fillers are used, how similar are the fillers, things like that. We also want to make it reproducible, so we're using the Ferret database, which is a publicly available facial recognition database that NIST published. And we're also planning on making the experimental materials available. We're also focusing a lot more on interactions and trying to move slightly away from the traditional paradigm of, okay, in an experiment, you hold everything constant except one thing. So now we're trying to look at, okay, what if you don't hold everything constant? What do these interactions mean? Another thing we're doing is we're taking repeated measurements from the same people. So trying to get a better idea of how different witnesses might get better at identifying or worse, and what their confidence distributions look like, and things like that. I'm also continuing some statistical methodology work with Stephen Feinberg and Anjali. And so this is kind of on the combining other evidence side, some Bayesian methods, some hierarchical modeling, and also developing an open source tool that includes multiple analysis methods and kind of if you change a thing, how do all the different methods change, and some data visualization to be available to researchers. So in conclusion, I've contributed an evaluation of some current statistical analyses, a log linear framework for lineups, and also some first steps of experimental design. And where we're moving next is more of the implementation and the dissemination. So that's all I have. If you have any questions, I'm happy to answer them.
Thank you for that presentation. I was, a lot of the things you were saying about the details of how to set up lineups, I think have been overlooked in the past. So, and I'm very interested in reading the dissemination statement. Just to clarify, one of the complications in the setups of different potential types of lineups. So the police have a suspect, and that suspect may be factually guilty or factually innocent.
Right.
So that's, and then there's the target present or target absent. So are we talking about whether the suspect is in the lineup, or whether the suspect is out of the lineup, or are we talking about whether the suspect who is factually the offender is in the lineup versus there's a suspect in the lineup who is factually innocent? Because there seems
The second one.
Okay, but
Yeah.
there seems, do they ever do lineups in which they know that they're all fillers?
No.
They don't.
No, I think that if you told a police department you should do some lineups where everyone is innocent, they would be like, that's a waste of our time. Why would we do that?
So when you say when it's target absent, it means there is a suspect.
There is a suspect, and that suspect is innocent.
Is innocent.
Right.
Other questions?
Do you have a feeling about, or anything to say about whether the choice of the filler should be based upon the suspect versus the description of the perpetrator?
So I do have some feelings. I can't say if they're totally backed up by anything, but I think that if a witness describes a suspect, you should not show them a suspect that does not match that description, and that I think the people in the lineup should match the suspect in the lineup rather than the description from the witness. If you had to choose.
Oh, you mean if the witness describes a perpetrator, right?
Right.
No.
Right.
We don't know yet whether they're the same person.
Right. Yeah. Sorry.
I have one minor point and one more serious question. The minor point is some of your ROC curves weren't on a unit square.
Right. Yes.
So they should be so that you get the right character. And then of course you do in the area.
Right. So they should be, but in lineups you can't get people to be confident enough to always pick the right person.
That was my next question. Would it be interesting to look at restricting analysis, say to those who had high confidence, whatever, versus low confidence, and look at their various ROC curves and see, for example, we might be able to say, oh, if somebody has a confidence level above so much, then it's working. Otherwise, it's almost like red point.
Yeah, I think that's a very good point, and I think that's kind of why we need to look a little more at repeated measurements, because some people will just be more confident. They just express their confidence as higher numbers, and other people are less confident, but they might actually perform the same in a lineup.
Just very quick question, and then we'll move on to the...
One, if you have an underlying model of how we recognize and memorize people, because, for example, we know that in Italy we say all Chinese are equal. Okay, but I think it is good. Then the second, you will talk about confidence level, but you will also say how much I'm confident. You are using your formula some kind of standard non-Bayesian formula, but you should know that the confidence level and confidence of the frequentistic formula do not mean how much you are confident. So if you are telling this to a jury,
Right. I tried to make that clear in the slides by calling the confidence of the witness the ECL, but I know when I talk about it, I kind of go back and forth, so thank you.
Thank you very much.